Okay, fine. So let's start. So thanks for giving the opportunity to give a talk here. So this is the subject of my talk. Okay, optical control of the anyway, it's optical control of something. Okay, this is done with my collaborator, former student Serguei Brazovskii, who is in New Hampshire. Anyway, the outline is this. First, I will discuss a general theory for dynamical Stark shift, the energy shift of a quantum system, in this case electrons in a crystal, in the presence of oscillating electric field. Okay, so this, okay, so this will be like the basic theoretical part. And then the rest of the talk will be applications to various systems. First, I will do quick to transition metal optical cogenites, and then most of the talk will be application to Chern insulators and the way to use optical control, optical means to control the sign of magnetization of Chern number and Chern insulators. And then I briefly discuss other materials and other ideas. Okay, so let us start with the first part. So the basic theory, if you like, which is actually quite simple, as you will see. Well, simple but not so simple, and known but not so well known. Okay, so let's start kind of pedagogical and consider the energy shift in an atom in the presence of oscillation electron field. So essentially, what we have some energy levels in an atom, and if you apply, let's apply interact oscillation electric field, and due to this oscillation electric field, well, it's weak oscillation field, so we can use it couples by dipolar coupling, electric dipole times electric field, and it produces two effects. It induces some non-zero dipole moment via this polarizability tensor, but very importantly, it also gives energy shift. So these energy levels in an atom will get shifted to the second order of electric field, and the coefficient here is polarizability tensor, because it's second order tensor in the electric field, so it's polarizability tensor, exactly the same one that gives you the induced electric dipole moment. So this is textbook thing, basically. Apply oscillation electric field, it produces energy shift of energy levels, okay, in an atom. In an atom is very well known. This is obtained, of course, by the second order perturbation theory, which is textbook quantum mechanics. So far, so good, right? But now let's consider the same story, not in an atom, but in a solid, in a crystal, okay, in a periodic system. So in this case, of course, there are energy levels, as you know, and they have actually discrete index n and continuous index k. So discrete index n is basically the band index, which is kind of qualitatively similar. It's discrete index, discrete bands, which is kind of similar to energy levels, discrete energy levels in an atom. But in a periodic system like a crystal, we also have quasi-momentum. So energy levels actually, they broaden into bands. So there is continuous quasi-momentum and discrete band index n. And of course, the wave function have the Bloch structure. Again, this is all textbook stuff. And the notation is the energy, the difference of energy between two bands. I will call it E epsilon and m just for shortness. Now we take this system, electrons in a crystal, and apply oscillation electric field, and calculate the energy shift of those energy levels to the second order of perturbation theory in the electric field. And it turns out that you actually get two kind of terms. Some terms are interband, and some terms are intraband. Okay, so the interband terms are qualitatively similar to what you get in an atom. So essentially what you have here is a second order perturbation theory. You have electric field, R is matrix element of electric dipole, and in the denominator you have energy difference between this level and this level, E and M, plus omega or minus omega, because it's AC frequency shift. So qualitatively, these interband terms are similar to energy shift in an atom. And by the way, the matrix elements of electric dipole actually bend barrier connections in a crystal. But anyway, a small remark. However, in addition, you have additional terms which are intraband, which do not exist in an atom, because atom doesn't have any bands, only crystal does. So here you also have additional contributions, second order in the electric field. And the coefficients here are the following. So, and you can classify them into symmetric and antisymmetric. This tensor can be separated, electric field tensor, into symmetric part and antisymmetric part. So symmetric term gives you this term, which I'll explain in the next slide, which is like inverse effective mass. And antisymmetric term, electric field, couples to another term, which is basically barrier curvature. This omega is actually barrier curvature of electron band structure. So you have two kind of terms, additional terms, symmetric and antisymmetric, which do not exist in atoms. So atomic physicists, AMO physicists simply don't know about them. They know exist only in crystals. So only solid state physicists should know about them, although to my knowledge are not very well known. Meaning symmetric term is known, but antisymmetric, I'm not sure. I mean, we may be the first one who actually described it explicitly, but anyway. Okay, fine. So let's discuss now the next 3 slides. I will briefly explain the origin of these 2 terms, and then I do applications to various systems. So first of all, very briefly about symmetric and antisymmetric, just a very brief nomenclature. All these effects proportional to the second order in the electric field. So this is second order tensor. This is amplitude of electric field. This is real, complex conjugated, use complex representation, of course. And this tensor you can separate in the symmetric part and antisymmetric part. Now, symmetric part is even with respect to time reversal, whereas antisymmetric part is odd. It changes sign upon time reversal operation. And this tensor is antisymmetric, so it can be equivalently represented in terms of a vector, and this is helicity vector. So this helicity vector basically can be written explicitly as a vector product of E cross E star. So essentially it's the angular momentum of light. So this exists only when light have non-zero ellipticity, like circularly polarized light. For linearly polarized light, it just vanishes. It has to rotate in some way. So if you have rotating polarization of light, it has non-zero angular momentum, and this helicity vector H is essentially, basically symmetry-wise represents angular momentum of light. Okay, fine. So this is so far the classification of electric field of electromagnetic wave. Now, there is similar classification of electronic, because we discuss coupling between electromagnetic field and electrons. For electron, now this is energy band of the electrons in a material. So it has bare energy dispersion, and it has second order correction due to light. And this all can be also separated into symmetric and antisymmetric, meaning with respect to momentum k. If electron system has time reversal symmetry, it can be only symmetric, energy dispersion must be symmetric. But if time reversal is broken by the presence of circularly polarized light, then it can also have antisymmetric correction to the energy dispersion of the electrons, okay? So this is just classification. So now let me explain separately to 2 slides the origin, qualitatively, origin of symmetric and antisymmetric energy shifts of the electrons in the presence of light. So symmetric energy shift. This is very simple. Let's just use Newton's equation of motion. This is time derivative of momentum. So if you apply electric field, it applies force. Force produces time derivative of momentum. And this is oscillating electric field. So the momentum of electron would oscillate around some equilibrium value with small amplitude, around some average value. And it follows from this equation of motion that the amplitude of oscillation in momentum space is basically proportional to electric field divided by frequency, omega, because it's time derivative. So anyway, so then you can calculate time averaged energy of the electron. So you say electron has momentum k, plus there is some small deviation, oscillation. You expand to the second order in Taylor expansion, first order, second order. Then you average over time. Linear term averages out because it's oscillates up and down. But second order term does not average to 0 because it's quadratic. And voila, you find second order correction to the energy dispersion. Okay, so it's quadratic to the symmetric part of the electromagnetic tensor, and the coefficient is proportional to second derivative of dispersion. This is basically the inverse effective mass. So this term essentially represents Newtonian inertia. Okay, electrons in crystal have inertia, although it's given by the curvature of the electron dispersion. Okay, and so that's why this term goes 1 over omega squared. This is also known as diamagnetic term, or like London term, or this is basically Newton's inertia. Now, what are the effects of this? One effect is actually, this is just for one band, but if you have, say, more bands, 2 bands, there is additional contribution coming from interband term. Remember in the first slide there was intraband and interband. Anyway, you get some formula. And most importantly, one effect of this oscillation in the electric field is actually flattening of electron energy spectrum. So for example, let's consider this kind of one-dimensional system just for illustration. It has some energy dispersion, okay, the bare energy dispersion. If you apply now oscillation electric field, so what happens? Essentially what this formula does, momentum now oscillates, and the electron energy gets averaged of this point and energies of the neighboring point. So basically, if we are at the top of the band, because of this averaging, the energy gets shifted down. If you are at the bottom of the band, get average energy gets shifted up. So basically, you get the dashed line, you get a flatter band. So in principle, applying oscillation electric field can in principle control flatness of the band, okay, and make it flatter. And that may be actually a useful tool for the experiment potentially, okay. But let me move on. My main actual interest is not in symmetric energy term, but antisymmetric, which is next slide, okay. So Now let's discuss antisymmetric energy shift in the presence of circularly polarized light. So now we apply electric field which rotates an electric field. Okay? And then again you solve equations of motion, and very easily you find that electron momentum essentially in the Brillouin zone in momentum representation just rotates on a circle. So there is some average momentum and then deviation that moves on a circle. It just follows from Newton's equation of motion. And the radius of the circle is again electric field divided by frequency omega. So bottom line, in rotating electric light, electron moves on a circle in the Brillouin zone. Okay, but now suppose electron has a non-zero, suppose band structure is such that it has non-zero Berry curvature. So every time electron makes a circle, it accumulates Berry phase. So Berry phase is basically Berry curvature times the area enclosed by the orbit, and that goes like E squared over omega. And the point is that as electron keeps circling and circling, it keeps accumulating Berry phase, and the phase increases linearly in time. But if phase increases linearly in time, in quantum mechanics, that means energy shift. So energy shift is phase accumulation per period. Okay? And then you plug numbers, you end up with energy shift proportional to Berry curvature, square of electric field, and frequency omega. So bottom line, circularly polarized light produces energy shift of electron proportional to Berry curvature at given momentum, in given momentum space. Okay? So this was just intraband term, but again, there is also interband contribution, which is similar. So if you combine them together, say for two band, you get basically the same formula with some coefficient, which depends on energy difference between the bands on omega. It reduces to this formula in the limit of small energy. Okay, so basically the story is like this. You have a two-dimensional system, and electron that moves in this two-dimensional plane in momentum space, it has Berry curvature vector, which is perpendicular to the plane, and it couples directly with helicity of light. So H is helicity of light, which is this perpendicular vector H. Okay, and it couples to Berry curvature and gives energy shift. And now from this point on, I branch into two applications. I'm more or less finished with the first part, the general theory. Now I'm going to use this for applications. Next slide, I will show applications to energy shift of just single particle energy states in transition metal decalcogenates. And then after that, I will show next thing the applications to twisted graphite and Chern insulators, because this is energy shift of one electron state with given K. But if you integrate over Brillouin zone, integrate this energy shifts of the whole Brillouin zone, you get energy shift of the whole sample. This is just thermodynamic energy shift due to circular light, and it's proportional to helicity of light H multiplied by the integral of this whole thing over the Brillouin zone, and this can be thought of as some kind of optical analog of magnetization. So anyway, so this is basically how the energy of the whole system gets shifted due to helicity of light, and some integral of the Berry curvature over the Brillouin zone with some coefficient. So I will apply this to Chern insulators. Okay. Yes. Yes. Yeah, so you see, this is the band structure, okay, and the band structure of the crystal reflects all the crystal symmetries. So whether crystal has inversion symmetry broken or not, it will be represented here. But you see, my focus here in my talk will be on time reversal symmetry breaking. There can be separate story about inversion symmetry, etc. There are many ways one can go. But in this talk, because I have limited time, I focus specifically on time reversal, and the crystal itself may preserve time reversal symmetry like TMD, we shall next slide, or electronic system may break time reversal symmetry spontaneously like Chern insulators. And that's basically the dichotomy I will want to focus. Inversion symmetry will not play much role, although it can be included, it's part of the story, but it's not my focus, okay? Okay, great. Let us discuss TMD materials. So, transition metal decalcogenides, you probably know they have hexagonal honeycomb lattice, so they have, like graphene, they have, two values, K and K prime, and they have pretty wide energy gap, okay? And so there are massive Dirac points at K and K prime points. They have non-zero Berry curvature. So the Berry curvature of these two Dirac points in TMD materials has opposite signs. So they do have non-zero Berry curvature, and it has opposite signs in the two valleys. Okay. Now let's take this system and shine circularly polarized light. Now circularly polarized light will couple to that Berry curvature and will produce energy shift of each band. Okay. So that's basically the formula. So you take you basically plug into those formulas I showed you in the first slide and apply them to massive Dirac points, and you calculate basically pretty straightforwardly energy shift of each valley. Now, the energy shift is different. So one valley, this dashed line is energy shift of each valley, and it's different because in denominator you have 2 delta, the energy gap, and this is plus minus h omega. So sigma is index of circle light, and s is index of the valley, is a product. So bottom line is plus minus h omega. So for one valley it's plus, so one valley will be like minus h omega is big shift, another will be plus a small shift. So energy shifts are different in 2 valleys, okay, if you shine circularly polarized light. Now the question is, can this be measured experimentally? Surely it can, and in a way it has been measured, although there are some caveats. There are well-known experiments done by the group of Gedik at MIT in 2017, where they actually measured energy shifts. However, there is a caveat. The caveat is that this system have excitons. And what they measured is actually energy shift of the exciton frequency, okay? So in other words, there is this exciton energy, and once you apply, it's called a pump probe experiment. You measure, this is a probe, you measure exciton energy in the presence of pump, is the presence of circle light of pretty small frequency, which is below the transition threshold. So you basically shine circle light, which is not absorbed, and then you shine second beam of light, the probe, which measures energy shift due to the pump, okay? So anyway, they measured energy shift of these excitons in the presence of background circle light, and they found actually very good agreement. So basically, this is a formula that very well describes their data. Essentially, it's again, there was a use second order perturbation theory, the square of electric field divided by 2 delta plus minus h omega, and they see perfect agreement. For one valley, they see basic energy shift goes like, gap minus h omega. For the other valley, it goes gap plus h omega. And the points scale for different frequencies of the background light. They scale very perfectly. So there's excellent agreement between measurements and theory. However, there is a problem. The formula that they use in their paper looks similar, but not the same as my formula, which I propose. You see, this part is exactly the same, square of electric field and denominator 2 delta plus minus h omega. The difference is in prefactor. In their case, prefactor is constant because they simply use second order perturbation theory. That means interband. They only took into account interband terms. They did not take into account, I think didn't even realize, the existence of intraband. If you do take into account intraband terms, those which are not so well known, I would say, you get prefactor which depends on frequency. And so the scaling should not have worked if this formula is correct. So how to resolve this contradiction? Well, our argument is the following, that they measured exciton energies. Excitons are bound state, and exciton is a neutral object. So total charge is 0, so there is no center of mass motion. So what I discussed, intraband terms are basically center of mass motion of the electron, Newtonian. But exciton is neutral, so there is no center of mass motion. So bottom line, for excitons, only interband terms work, and otherwise there is agreement. But there should be also interband. For this purpose, you should measure not excitons, but we really need to measure band edge shift. So in other words, there is difference between shift of excitons and shift of band edge. And this, I think, can be measured using electrostatic gating. Basically, you can put, chemical potential here and see, you get some conduction pocket, and then you apply light, and one gets pushed out, and this pocket disappears, etc. So it should be measured, I think, by combination of electrostatic gating and optical probe, which I think are the main themes of this impact series of conferences. So this experiment, as far as I know, has not been done, and I hope somebody will do it. Okay, but anyway, yes, go ahead. Yeah, okay, so there are, you see, the point is this is a pump probe experiment, so there are 2 frequencies. So this A omega is what I call background frequency. So you take your system and shine light at relatively low frequency. I mean, frequency way below absorption edge. So it's called sub-gap frequency. So this light is not absorbed because it's sub-gap, but it produces energy shifts of the electrons. And then you shine probe light to probe the shift of the electron energies. Yes, okay? Okay, fine. So this was single electron picture. This is discussion shift of just one particle energy, single particle energy. But now let's now integrate over the whole Brillouin zone and consider. And the way that TMGs, of course, do not break time reversal symmetry, so that's why you have 2 values. The effects are opposite for 2 values. Now let's consider a different story and different system. Now we're talking about switching to Chern insulators. and twisted graphene bilayers on boron nitride. So this is, of course, a very interesting system, a lot of studies, and lots of things observed. But I focus specifically on Chern insulator story. So I'll briefly walk through this in one slide. So this is based, it was measured by different groups. This is from Andrea Young from Santa Barbara, but these things were done in different groups. So anyway, this is resistance measured interlayer, resistance as a function of doping, okay, of gating, okay. So these are different filling factors, 1, 2, 3, 4, I'll explain in more detail. At filling factor 0, you have just trivial insulator. At filling factor 4, you also have trivial insulator, I've explained. But at filling factor 3, at the odd filling factor, we observe a non-zero hole resistance, which appears spontaneously in the system. So at odd filling factor, like 3 or maybe 1 in some other cases, a system spontaneously breaks time-reversal symmetry. It breaks Valley symmetry, I will explain in a moment. And it develops spontaneously non-zero hole resistance without any magnetic field. And you don't need to apply magnetic field. So it's basically anomalous quantum Hall effect that appears in the system spontaneously. This is basically Hall resistance as a function of magnetic field, and you see hysteresis. Okay, so if you apply external field, of course, you can switch the sign of the Hall effect between, say, plus and minus, but here you have hysteresis. And if you're at zero magnetic field, there are two possible states with either plus or minus Hall resistivity. This is Chern number being plus minus 1. And this, in some sense, you can think of as a topological memory. System says in this state is 1, this is minus 1. So in principle, you can use Chern number as a topological memory. Okay, and this, of course, this system is orbital ferromagnet. This comes from orbital effects, I'll explain in a moment, not due to spins. And it's ferromagnet because it's either up or down, plus or minus. This is a symmetry. So anyway, first of all, this transition happens at certain temperatures, like say around 7.5 Kelvin. There is a well-defined transition temperature below which time-reversal symmetry breaks spontaneously, like in any ferromagnet. There is activation gap, so this phase transition opens energy gap. There is activation gap. And this is basically the qualitative picture. It's not my figure, it's taken from, it's a theoretical sketch I copied from experimental paper. So basically, this is two values, one value, another value. This is like the Dirac energy, but because you have electrostatic gating, and Fermi level is here. So you have basically two values. One value with Chern number plus and minus, and for each value you have spin up and down. So the total filling factor is 4. So this filling factor 4, all those mini bands are occupied, so it's a trivial insulator. This is this situation. But now let's say we decrease filling factor, okay, to filling factor 3. So now we have to partially depopulate those bands. And of course, system could in principle have partial population, but systems don't like this because of Coulomb interaction. Yeah, because of Coulomb interaction, they prefer to bands either completely occupied or completely empty. So essentially spontaneously breaks symmetry between values and pushes one band above the Fermi level. So basically this value is now, this band is depopulated and this is populated. So now system spontaneously breaks symmetry between values. Okay, so for one value, both bands are occupied. For another value, only one is occupied. So there is asymmetry, which is spontaneous symmetry breaking. And those values have different Chern number, so it has non-zero Chern number. So essentially, the picture is like this. You have two values, usual story of second-order symmetry breaking. Okay, so far so good. That's a brief summary of the origin of Chern insulators on those materials. And now let's get to optical effect. So again, this is the same story. The symmetry is broken between two values. One is occupied, well, one is partially occupied. So now you have non-zero Chern number between these two bands, this and this. And so what are the consequences? One consequence, of course, quantized Hall conductivity, very well-known effect. Hall conductivity is just integral of Berry curvature of the whole brilliant zone, and this is Chern number. But there are other consequences. For example, orbital magnetization. There is some other integral of Berry curvature, gives you magnetization. And this is orbital magnetization, because spins play no role here. Spins essentially play no role in this story. And of course, there is energy, if you apply external magnetic field, there is usual energy of interaction magnetic field with magnetization. But also now, if you apply now circularly polarized light, there is energy of interaction between circularly polarized light as characterized by helicity, H, and another integral of Berry curvature of the brilliant zone, which gives me what I call the like optical magnetization. It's optical analog of magnetization. It has the same structure here. So H, the helicity of light, plays the role of effective optical magnetic field, and it's multiplied by some object, which is an integral of Berry curvature, with an optical analog of magnetization. But you see, it depends on frequency of light that you shine. Okay, fine. And so this energy of interaction with light can control the state of the system. So we might ask the following question: oh, there is effect. There should be this effect that may be weak because the intensity or fluence of light can never be too big. You don't want to burn your sample in your cryostat, so it's always limited. So it may be a small effect. Well, it depends. Actually, near the second order phase transition, this term actually dominates. Because you see, according to the Landau theory, near the transition point where systems break symmetry spontaneously, the energy has quadratic term with coefficient T minus Tc and quartic term. So basically, near Tc, the energy is quadratic in magnetization, but this term is linear in magnetization. Okay, so that means the interaction with light is like always strong in the vicinity of phase transition. Okay, because that's where system works. So that can be used to train the system. That's basically the picture. Break symmetry. The presence of light breaks symmetry between the two values externally. So then basically the circularly polarized light can be used to train the state of the system. So in other words, let's say we cool down. Let's say this is time. We cool down system starting above Tc, above transition temperature, in the presence of circular light. So we decrease temperature. The sample one system reaches transition temperature. At this point, the presence of circularly polarized light tells system which way to break symmetry, go plus or minus. At this point, non-zero Hall resistivity appears with the sign plus or minus, and the sign of the Hall resistivity is controlled by light that was present. Then you could turn off the light, and system stays in the same state. So basically, you can use light to control the sign of your Chern number. That means the sign of your memory, if you like. Moreover, you can in principle shine two beams of the opposite circular polarization. They will nucleate two domains with opposite Chern numbers, and between there will be chiral channel, chiral one-dimensional channel, etc. So that's how. That's basically that's more or less the end of the second part of the talk. Optical control of Chern insulators. And now in the remaining time, I'll go briefly through other systems. Yes, go ahead. Yes, go ahead. Mm-hmm.
So there is just one thing, since we did this experiment now for quite, for almost a year,
Uh-huh.
we've been doing this experiment.
Mm-hmm.
The biggest problem is that when you shine light,
Mm-hmm.
you also excite carriers, and even at these temperatures of 7, 8, 9 Kelvin,
Mm-hmm.
these carriers stay. So you are not at the same doping that you think.
Mm-hmm.
You're not at the same gauge that you think.
Mm-hmm.
So what you get actually, and that's one of the reasons we never published it,
Mm-hmm.
is the first pass, it works,
Mm-hmm.
and then if you try to go back and forth,
Mm-hmm.
it doesn't work
Mm-hmm.
anymore because you are
Mm-hmm.
basically already saturated your system.
Yeah.
It's very complicated, and if you reduce the power of light,
Mm-hmm.
you don't have anything.
Mm-hmm. Mm-hmm. Yeah, I see. There is a problem. See, because again, my theoretical condition was kind of idealized. So I basically implicitly or explicitly assumed. I mean, the best situation would be when you have big energy gap, and shine light at frequency which is much smaller. So that is not fair. However, for graphene, of course, the gap is very small. Gap is very small. So specifically for graphene, because of smallness of the energy gap, it's really difficult. You shine light, you excite carriers, that messes up everything. So yeah. But I'll show you some other examples for other systems where gap may be bigger, not graphene, but and they may work better. In fact, I'll just mention some examples. Okay, fine. So other materials. So yes. Can you say it louder?
So when you do this controlling of this heaviness of the polarized
Yes. Yes.
direction, so do you always need to, at some point in time, do you need to close the gap?
No. Okay, so basically what happens is this. We start above transition temperature, okay? So you start in a normal metallic state, above Tc, okay? And you then cool the system, you decrease temperature, cool the system, in the presence of, well, relatively weak circularly polarized light, which hopefully is not absorbed if system, yeah, that's a problem. Yeah. Ideally, you want a gap, and ideally want this light not to be absorbed. Okay, then you decrease temperature, and then there is phase transition where system spontaneously breaks time reversal and becomes Chern insulator. That's where Hall resistance develops, and the sign controlled by light. But ideally, I would prefer light not to be absorbed. But in practice, it may be absorbed, and that will be a problem. I mean, it may create problems. In fact, it does. Okay? Okay? Okay, so let's move on. So very quickly in the remaining time, other systems. First of all, Chern insulators and other materials. You can have Chern insulators not only in graphene, but also in TMD. That was just mentioned in the previous talk. You take two different TMDs, and create moiré patterns between them. This was done by a group at Kinfaimak at Cornell. And they basically do observe quantum Hall effect somewhere in the corner. They control gates, and they do observe quantum Hall effect. This is Hall resistance as function of semagnetic field, and you see the hysteresis, which develops at low temperature. So one can have Chern insulator in TMD materials. That's another system one can try. And in principle, in Cornell, I think they do have optics, so I mean, they should be able to do this. I mean, I talked to him, but I haven't heard any measurements along those lines. But they should be able to do it in principle. Anyway, that's TMGs. The other system is more controversial. This is Kagome materials. I will not talk too much about it. There was some let's see, what is this? There was some experiment suggesting that these Kagome systems break time reversal symmetry around 80 Kelvin, but it's controversial, experimentally controversial. And the band structure of these Kagome systems, it may have flat parts of the Fermi level, which of course have nesting to create three charge density waves, and if those three charge density waves have appropriate phase, shifts, etc., those charge density waves, three of them, could in principle break time reversal symmetry and produce then, I guess, something like Chern insulator. But this is all very open. This is speculations, both theoretically and experimentally. So anyway, I don't want to speculate too much about this. This is hypothetical, may not work, But let me move to this is my second to last slide. 2 more slides and I will be done. Very briefly, how optical control may work in other materials. This is a theoretical paper. Apparently, there was earlier paper in Nature, which I should check. This is theoretical proposal to use the same idea, circularly polarized light, to control time reversal break-in superconductivity. So there are superconductors that may materials where superconductivity breaks time reversal symmetry. So Aaron Kapitulnik did a lot of work on this. And the sign of this time reversal break-in can be controlled by what's called training field, which is usually a weak magnetic field applying to tell system which way to go, plus or minus. But instead of that, circularly polarized light could be used for this purpose, and Aaron told us it's very difficult to do experimentally because gaps are very small, so other carriers are created. But anyway, so there are some other systems where there is some optical control, but in a somewhat different way. I just mentioned them very briefly. I don't have time to go into any details. So this is called, axion optical induction interferomagnetic order. So essentially, you take even layer magnetic or interferomagnetic, specifically topological insulator. And so it was demonstrated experimentally by the group at Harvard that that system, it has non-zero magnetoelectric effect. And this magnetoelectric effect also has some sign. It has a sign. And the sign of magnetoelectric effect can be controlled by circularly polarized light. And this was demonstrated in this paper, theoretically and experimentally. Okay, so I'll move on. I don't want to spend more time. Another paper, much earlier, this was relatively recent. This is much earlier paper, again, by the group of Gedek. They used this TMD material, titanium selenide 2, and they discussed spontaneous gyrotropic electron order in this material. So what basically happens in this system breaks chirality. It does not break time reversal symmetry, but it breaks chirality. And essentially, the way it does, one proposal actually was made by Van Wezel quite often in this Cargèse series of conferences. Essentially, there are like 3 charge density waves, and they produce some kind of, with appropriate phase shift, they produce some kind of spiral structure. And they have a spiral like DNA, etc. It breaks chirality, and this spontaneously, and the sign of this chirality, this is about inversion symmetry break, that includes inversion symmetry break-in. That can be controlled by circularly polarized light, although in this case it's related to non-zero momentum of light. It's called space dispersion. You need to take into account that light has non-zero momentum. So again, and also in cuprates there was discussion of this, okay. Anyway, another story, this why I mostly focus on orbital magnetism, but you also can have spin magnets, because you have spin magnets, and you can take 2-dimensional Ising spin, molecular layer, two-dimensional magnet which includes iron, which has magnetism, Ising-type magnetism, and this Ising magnetism can be controlled by circular polarized light. This was done at Maryland by a group of Chern Gong. Okay, still being have difficulty getting published it. Okay, and this is the last part which I hope I have a couple of minutes to discuss. Of course, control of magnetism, optical control of magnetism is a very big subject in general. People really like to control magnetism by light. And there are many papers, and I want to focus on this one. This is chromium iodine 3, again, atomically thin, chromium is magnetic iron. It has odd number of layers, so it's a ferromagnet, and the sign of magnetization can be controlled by light. So I show one more slide and we'll be done about this paper. This was done at Berkeley. So this basic material is basically ferromagnet. It's anti-ferromagnet, up, down, but you have odd number of layers. So effectively, it's a ferromagnetic layer. And what they found is that they shine light with positive or negative, well, right or left polarization. They produce switching. They can switch. They send pulses, intense pulses at low temperature, and they switch direction of magnetization. But interestingly, that if you say right polarized light, it only switches in this range of frequency, below 2.1 electron volt. If you will shine light above 2.1, you have to use the opposite helicity. So bottom line, depends on frequency of light. You produce switch. To produce switch, you need different opposite helicities, which is kind of strange. For momentum conservation, if your spin is up, you want to flip it, you might say, oh, I need to change momentum. But then you use only one chirality. In this case, it's a different chirality. So in a nutshell, I really ran out of time. This is an explanation, and it's related to principle of maximal entropy production. This is our new theory, which is not even written. It's a speculation. So this is calculated energy spectrum, which is also discussed in a way in this paper. So this is antisymmetric polarizability or permittivity, and it has absorptive part. This is absorptive part, and this is non-absorptive part. And basically, because system is magnet, it has, right and left circularly polarized light is absorbed at different frequencies. And so essentially what happens is the following. The ferromagnet flips magnetization in order to maximize absorption. Or put it a different way, system, because it's a highly non-equilibrium system, you send very high intensity of light, it's not equilibrium thermodynamics anymore. And if it's non-equilibrium thermodynamics, according to some proposal for whatever, system operates, chooses state to maximize entropy production. That means to maximize dissipation. So here is the deal. Suppose you shine light at this frequency, 1.10 electron volt, somewhere here, okay? And at this frequency, let's say left light is absorbed, but right polarized is not absorbed. So you send right polarized light. You send right polarized light. It's not absorbed because there is mismatch. But if system flips magnetization, these things interchange and light becomes absorbed. So in other words, if light is not absorbing for this polarization, system would flip magnetization to make it absorbed. Okay, so that's why we have this. On the other hand, if you have this frequency and shine right polarization, it's already absorbed, so there's nothing to switch. There's no reason to switch. On the other hand, okay, finishing. Yes, if you shine negative, it will switch. So bottom line, this system is highly non-equilibrium. So I think in this case, behavioral system is controlled by dissipative part of electric permittivity, whereas the story I told you in the first part was quasi-static. You cool it down very slowly, so it's quasi-static thermodynamics, which is controlled by minimization of energy rather than dissipation, is controlled by the real part, meaning by the non-dissipative part. And non-dissipative part does not explain this experiment. It's dissipative part which does. So one should be careful. If it's non-equilibrium, look at dissipation. If it's quasi-equilibrium, look at non-dissipative equilibrium part. So these are my conclusions, and I am our time. So thank you very much for your attention.